To begin our understanding of inter-network communications, let's review the 3 Ps. The first P is packet, a logical container representing the flow of data. The second P is protocol, a language and set of rules that network devices operate by. The third P is port, a numerical designation representing a particular protocol. What is a packet? A packet or datagram is a logical representation of a physical phenomena. It forms a unit of containment whereby data can be examined, routed, and filtered in regards to its destination, source, and content. The following diagram figuratively represents a datagram packet on a network. This table represents a 32-bit IP version for packet and shows it from a host named the Black Pearl to a host named the Jolly Roger. If you look at all of the different fields in this table, each one represents a field inside of a header, as well as the encapsulated data payload. You can see that the IP source address is 199.77.77.77, and the destination address is 199.77.77.69. This next table represents another packet, in this case a reply packet, returning from the Jolly Roger back to the Black Pearl. It is also 32 bits and IP version 4, but if you look at the source address and destination addresses, they are inverted. The previous diagram is not a real packet, but it visually represents the flow of electrons or photons that physically transmit data on a network. To our naked eyes, we are only speaking of variations in the flow of electrons. Photons are RF that modulate in amplitude and frequency and would only be visible to us on an oscilloscope. An example of some oscilloscope signals would be to reiterate, data transmitted on a network is really just a flow of electrons. As with category 6 and 5e, are photons, such as fiber, or RF when using 802.11 wireless, that modulate in both amplitude and frequency. These modulations are governed by the limitations of the media in which these particles travel. For example, electrons and photons attenuate, that is, they are absorbed, after a period of time into the conductors that carry them, such as copper wire or fiber. Here are some examples of photon and electron attenuation. In the attenuation process within a closed system, since no conductor is perfect, a certain amount of the flow of particles converts to an irreclaimable form of energy known as entropy, which is waste heat that irradiates outward from the conductor. Other sources may interfere with transmitted data as well, such as electromagnetic interference or EMI from power lines and lights, RF from cell phones and transmitters, and damaged connections and equipment. How do we define entropy? Entropy can be defined as an integral measure of random thermal energy redistribution due to heat transfer or irreversible heat generation within a system. Take a look at this diagram. In the diagram above, areas of disproportionate density and connected compartments filled with a gas tend to seek equilibrium. That is, the molecules in the area of higher density will tend to flow into the area of lower density until both sides have approximately an equal number of molecules or density. And here's just some cool pictures dealing with entropy that I kind of threw in for fun. Cumulatively, because of these effects, different media have different ranges and different bandwidth capabilities. Take a look at the following table. The first row depicts 100 base T or fast Ethernet, which has a range of 100 meters, a speed of 100 megabits per second. It's referenced via category 5, 6, or 7 unshielded twisted pair and RJ45 ends. Its medium is copper wire, and it requires 4 wires. Look at the next row, 1000 base T or gigabit Ethernet. It too has a range of 100 meters. However, the speed is 10 times that of 100 base T at 1000 megabits per second. It too utilizes category 5, 6, or 7 unshielded twisted pair and RJ45 ends. It also uses copper wire for its medium, and it requires 4 wires. Now the third row is something completely different. Wireless, or 802.11 A, B, G, or N, also known as Wi-Fi, operates in a frequency range between 2.4 and 5 gigahertz. It has a range of between 20 and 70 meters, depending on its frequency. It has a speed of between 11 megabits per second to 300 megabits per second, depending on whether it's A, B, G, or N. It's referenced as wireless or Wi-Fi. The medium is RF, and it requires a transceiver. Now look at the fourth row, 100 base FX. It has a range of 412 meters, a speed of 100 megabits per second, It's referenced as fiber. The medium required is multimode fiber, and it's simply fiber optics. Finally, look at the last row, 1000 base LX. It has a range of 10 kilometers. It has a speed of gigabit or 1000 megabits per second. It's also fiber, or it's referenced as fiber. It uses a 1300 nanometer laser. It's single mode fiber instead of multi-mode fiber, and it also requires fiber optics. To handle these errors, fields in each packet hold a CRC or cyclical redundancy check value that is calculated by an algorithm before they are sent. When those packets arrive at their destination, another checksum is calculated. If it matches the CRC field data from the source, the packet is good. If it doesn't, the packet is bad and is resent. When multiple devices transmit messages on a network simultaneously, various protocols must be followed and applied to packets on that network. For instance, carrier sense of multiple access and collision detection governs collisions, where multiple devices transmit simultaneously on the same medium on a cabled network. Carrier sense of multiple access and collision avoidance does the same on a wireless network. Without packet switching or bridging, all hosts connected on a network are placed within a single collision domain. All communication that takes place within a single collision domain must share limited resources, since any two devices attempting to communicate in that domain cannot transmit a signal on their media, be it copper wire or fiber, at the same time. Each device must wait for a turn to transmit its signal while the recipient device listens to the transmission. During this process, other devices cannot transmit. Once again, to facilitate sharing between hosts in a single collision domain, the carrier sense multiple access with collision detection, or CSMA-CD protocol, operates within each device. The basic processes of CSMA-CD are as follows. First, before transmitting, the device ascertains there is no signal currently flowing through its connection media. If the flow of particles is detected, it will not transmit, since doing so would corrupt the organized sequence of packets making up the data flow of the current transmission. If no flow of particles is detected and the coast is clear, the device will begin transmitting. During the transmission process, the device continues to monitor the media to which it is connected to make sure that no other devices are transmitting while it is. Second, if the device sending the signal detects another device transmitting in the same collision domain, the collision is said to have occurred. This corrupts and interferes with the sequence of packets being sent from one host to another. When the transmitting device detects a collision, it sends out a jam signal and all devices in that collision domain stop transmitting. They each wait a random interval before attempting to retransmit. In this way, multiple devices can time share the same collision domain. The problem with this method of controlling collisions is its inefficiency. Every time a collision occurs, every device in the domain must stop and randomly restart, and this can happen many times per second between multiple hosts. The end result is that many packets are interrupted and must be resent, resulting in slow data transmission speeds, network congestion, and time-consuming collision delays. Behold, the 7-layer Open Systems Interconnect model! Internetworking is broken into 7 conceptual layers. These 7 layers are known as the Open Systems Interconnect OSI model. The OSI model was created to allow vendors to manufacture components that meet the conditions necessary at one layer to interface with components at another layer. You might also use it as a diagnostic approach when troubleshooting. Let's examine each of the OSI's 7 layers. The first layer on the bottom is the physical layer. It would be things like hubs, cables, wiring, and media. Examples are Ethernet, RJ45, and 802.5. On top of the physical layer, the next layer would be the data link layer. Here are things like switches, MAC addresses, and error detection, though not correction. Examples would be ATM and frame relay. The next layer up is the network layer. At this layer, the third layer, routers, routing, and subnetting take place. Examples would be things like the IP protocol. The next layer, the fourth, is the transport. Here, packet ordering, reassembly, and error correction after error detection take place. Examples of things that happen at the transport layer would be transmission control protocol and user datagram protocol. Next is the fifth layer, which is the session layer. And here is sequencing and authorization. Examples would be RPC and NetBIOS. The sixth layer is the presentation layer. and at this layer, data formatting and encryption happen. Examples would be HTML, JPEG, GIF, and ASCII formatting. Finally, the seventh layer, the application layer, is where operating systems, user interfaces, and programs operate. Examples would be things like FTP, DNS, and a web browser. Each layer of the OSI encapsulates its data with PDUs, or protocol data units, that add that layer's information and flags to the header and trailer of the data field being carried by that packet or datagram. When sending a packet, PDUs are added as information, and field data encapsulates the program as it travels down each layer and is finally sent to its destination. Upon receipt of a packet, the PDUs for each layer are read from the header and trailer of the datagram, and those values are stripped off as the packet is passed up to each subsequent layer. Let's examine each of these 7 layers in greater detail. Layer 1 is the physical layer. This layer is responsible for sending and receiving bits through various connection media like copper wire, such as category 6 and 5e, and fiber optics like FIDI, via streams of electrons or photons that vary in amplitude and frequency to form a sequence of packets. Active hubs, or repeaters, which amplify and regenerate signals, operate at this layer of the Open Systems Interconnect model. Examples of physical layer standards are Ethernet 10 base T, 100 base T, and 1000 base T, FIDI, or Fiber Distributed Data Interface, 802.11 A, B, G, or N, ISDN, USB, IRDA or infrared, Bluetooth, FireWire, etc. Let's take a look at some specific examples of the physical layer. This first example is Ethernet. The transmission medium is copper wire. The transmitting particle is the electron. In this example, host A, hostname Galactica, sends a stream of electrons that modulate to host B, hostname Pegasus. These are connected via RJ45 connectors and the copper wire. In the next example, we're using fiber, and our media is FIDI, and our transmission medium is fiber optics. Our transmission particle is the photon. It's no longer the electron, since we're dealing with light. In this case, host A has an emitter that fires off a stream of photons to host B, which has a receiver. Finally, in our last example, we're using wireless, or 802.11 or Wi-Fi. The media is 802.11 A, B, G, or N wireless. The transmission medium is an RF signal, and in this case, it's not a particle, but it's radiation, RF and microwave. And in the example, host A has a transceiver, and it's simply modulating and sending RF energy out that's being received by host B. In addition to media considerations, with Ethernet there are 2 subclassifications. The first, half duplex, uses 2 wires. Collisions occur, and CSMACD must handle those collisions. 10 base T at half duplex would actually render approximately 4 megabits per second. The second, full duplex, uses 4 wires and creates a point-to-point connection between the transmitter and receiver. Transmit and receive wires are different, so when a signal is sent down the wires, no collisions occur. It doubles bandwidth, so 10 base T at full duplex renders 20 megabits per second, and 100 base T at full duplex offers 200 megabits per second. Now let's examine the second layer, or the data link layer. Layer 2 involves switching and MAC, or Media Access Control, addresses. A MAC address is a 48-bit or 6-byte hexadecimal value that forms a unique and usually permanent identifier for each device on a network. We say usually because this is not always so. Software can be used to spoof the MAC address on devices, and in addition, there are some devices that can actually have their MAC addresses reprogrammed in EEPROM or non-volatile memory. Switches read packet frames and determine where to forward them based on their destination MAC addresses, retaining the address of each device connected to their ports and their filter tables. They then use ASICs, or application-specific integrated circuits, to create separate connections and collision domains between any 2 hosts connected to their ports. This allows many hosts to simultaneously communicate. Here we have a 10-100 1000 megabit per second layer 2 switch, or gigabit switch. Here we have 4 hosts. We're going to connect the 4 hosts to 4 ports. This is a 16-port switch. This switch has a MAC table, and each one of these is going to be placed in its own collision domain. In this example, host A and B and host C and D can communicate in their own separate collision domains simultaneously due to the layer 2 switch's ASICs and MAC filter table. Full duplex communication can take place between each set of hosts without causing interference with other hosts on other ports. In this example, we can see half duplex, where when two hosts are communicating, they must share transmit and receive lines. In the next example, we can see full duplex, or 4 wires. In this case, each host can have its own transmit and its own receive. Here we have an example of a layer 2 Ethernet frame. This Ethernet frame has 6 fields, and each field has a purpose. The first, the preamble, is a 5 MHz binary clock allowing the recipient to lock the bit stream. The next two, the destination and source MAC addresses, are required for the packet to leave its source and reach its destination. The next one, or type, identifies the network layer protocol being utilized. The fifth, or data, is the packet from 64 to 1500 bytes. Finally, the last is the frame check sequence, or FCS, at the end of the frame, and it stores the CRC, or cyclical redundancy check checksum value. Also, tunneling is sometimes employed when using layer 2 Ethernet frames. In this case, one frame is encapsulated within another. Now let's examine layer 3, or the network layer. At this layer, routers route packets to different subnets based on their field data using static routes and dynamic protocols like Routing Information Protocol and Open Shortest Path First. Logical addressing and subnetting allow larger networks to be broken up into separate broadcast domains here. Note that at layer 3, broadcast domains are broken up, and at the lower layers, collision domains are broken up. At this layer, the IP protocol functions, both version 4 and version 6. Route update packets are sent from router to router to provide the means of getting traffic from one subnet or network to another. Whereas IP provides the routing, Transmission Control Protocol, or TCP, provides reliability and error correction. Both of these protocols together help create the TCPIP stack. Here we have a layer 3 router. Inside the router is a routing table, and it learns adjacencies, subnets, and other networks in the same way that a layer 2 switch would learn MAC addresses in its MAC table. In this case, the first network, 192.0.7.13, is an IP version 4 Class C. The second network is an IP version 4 Class B, 172.17.48. Through its routing table, the router can route traffic from the Class C network to the Class B network, and vice versa. Let's take a look at layer 4, the transport layer. At this layer, data is segmented and reassembled into streams. TCP, or Transmission Control Protocol, and UDP, User Datagram Protocol, function at this level. The transport layer implements flow control, and any segments that are not acknowledged as received by the recipient are resent by the sender, so that in this way TCP can ensure reliability. This layer also ensures that the transmission rate of the sender does not exceed the buffer capacity of the recipient. Source and destination ports are assigned here. Let's take a brief look at the encapsulation and de-encapsulation process. In encapsulation, a packet is given a sequence number and the CRC is calculated on the sender before that packet is sent to the recipient. When this process is complete, it's sent. Finally, on the other side, the de-encapsulation process begins. The received packet sequence number is checked and a CRC is verified against the same which was calculated on the sender. If they match, the packet is good. If they do not match, the packet is bad, and the recipient will send a request to the sender to resend that packet. Let's look at another example. In a firewall, the flow of data known as traffic is governed by standard protocols that bind to specific ports. Each port is represented by a number and can be filtered by opening or closing these ports to accept or reject packets whose field data match that port. The firewall controls the ports on its network interface whereby packets can enter, pass through, or exit. Ports can be opened or closed for each service or kind of traffic one wishes to allow. Other ports are closed for traffic one wishes to deny. Let's look at some commonly used TCP and UDP ports. FTP utilizes TCP 21 and 20, SMTP 25, SSH TCP 22, POP3 110, Telnet TCP 23, IMAP 143, Web HTTP TCP 80, and VPN 1723. SSL or HTTPS uses TCP 443, Kerberos 88. DNS uses UDP 53, SNMP 161.62, DHCP UDP 67 and 68, Samba 137 to 139 and 445, NetBIOS 137 to 139, Active Directory 445 for NetBIOS. Now we'll examine layer 5, or the session layer. Here sessions are set up, maintained, and torn down between communicating devices. Layer 5 coordinates communication and dialogue between network devices. In so doing, it keeps the data of different devices and applications distinct and separate from the data for other applications and devices. This is the layer that provides simplex, half-duplex, and full duplex options for hosts and clients. Next, we'll look at Layer 6, the presentation layer. Layer 6 translates and formats data according to various protocols and standards so that it can be presented to the application layer. It also provides translation services so that the data sent by the application layer of one system can be read by the application layer of a different system. This involves implementing certain standards, for example ASCII, or American Standard Code for Information Interchange. Many facets of compression, encryption, and multimedia streaming happen at this layer. Layer 7, the application layer. This layer is the part of the OSI model that interfaces with actual applications running within the operating system, such as a web browser or word processor. The layer itself is not an application, but it provides an interface to applications so that they can send data through and receive data from the other layers via the encapsulation and de-encapsulation process. Examples of other programs that interface with the application layer would be email clients, remote desktop software, and databases. Let's further examine the OSI layer encapsulation process. When encapsulation takes place on the sender, a packet starts out at the highest layer, the application layer, and travels down through the lower layers to the physical layer, where it is finally sent out across the network media. When that packet arrives at its destination, it then goes through the de-encapsulation process, and this is simply encapsulation in reverse. It starts out at the lowest layer and travels upward to the top layer. Here's another perspective on the encapsulation process, where different processes and objects are associated with different layers of the OSI. At the top three layers, layers 7, 6, and 5 are application, presentation, and session, we have protocol data units, or PDUs. At layer 4, the transport layer, we have segments and a TCP header. At layer 3, where routing takes place, we have packets and IP headers. At layer 2, the data link layer, we have frames, logical link control, and machine access control, or MAC addresses. Finally, at the physical layer, we have bits. Let's look at different types of Ethernet cabling. The first example here is a straight-through Category 5E unshielded twisted pair cable. If we look, only 2 pairs of wires are used, 1 and 2 and 3 and 6. The other 4 wires are not used, that is 4, 5, 7, and 8. It's DC current, and a flow of electrons passes down each of the 4 wires. Notice that transmit has both a positive and negative, and receive has both a positive and negative, just like any DC circuit. Some organizations use the remaining 4 wires for telephone wiring or a separate data network. Each end of a Category 5E cable terminates at an RJ45 end. The wires connect transmit to transmit and receive to receive and do not cross. Instead, crossover circuits and hubs, switches, and routers connect transmit to receive and receive to transmit. Since there are no crossover circuits when connecting one host to another without a switch or hub, this kind of cable cannot be used to directly connect 2 devices. For that, a crossover cable is required. The next type of Ethernet cabling we want to look at is a crossover cable. In this case, we have Category 5E unshielded twisted pair cable. Notice that the ends are inverted, so you have one normal end, and on the other end, you cross over transmit to receive and receive to transmit. Like a straight-through cable, only 2 pairs of wires are used, 1 and 2 and 3 and 6. The other 4 wires are not used, in other words, 4, 5, 7, and 8. Each end of a Category 5E crossover cable terminates in an RJ45 end piece, just like a straight cable. The wires connect like so, transmit to receive and receive to transmit. They cross over each other on opposite sides. This kind of cable can be used to directly connect network devices without going through a crossover circuit, because essentially it is a crossover circuit. Another type of Ethernet cabling is a rollover cable. Again, in this case, Category 5E unshielded twisted pair. One side of a rollover cable is normal, and the other side simply inverts every single wire. In this type of cable, all 8 wires cross over each other on opposite sides. This kind of cable can be used to connect a PC, laptop, or tablet to a Cisco router via its serial console input port. The router may then be connected to via a terminal emulator on the PC, such as Hyperterminal. In addition to the Open Systems Interconnect hierarchical conceptual 7-layer model, Cisco has its own 3-layer hierarchical model. The first of these layers is the core layer, or the backbone. It has 2 primary functions, 1 to transport traffic reliably and quickly, and 2 to switch data as quickly as possible. The second layer would be known as the distribution layer, or the routing layer, aka the workgroup layer, and its primary function is filtering and wide area network access. Finally, the third layer would be known as the access layer, and its functions are switching, user and workgroup access, access control, policies, and collision domain configuration.